There's something out there in the vast darkness of space, something we can't see, can't touch, and yet it holds the very fabric of our universe together. Imagine a force so powerful it shapes galaxies, bends light, and makes up over 85% of all matter in existence, and yet we've never actually laid eyes on it. This is the enigma of dark matter, the cosmic ghost that haunts our understanding of the cosmos. For decades, scientists have been chasing its shadow, piecing together clues from the way galaxies spin too fast, from the way light warps around invisible masses, from the way the universe itself seems to be held together by something we can't even detect. And at the heart of this mystery, the dark matter halo, a vast, invisible structure wrapping around galaxies like a silent, unseen hand. But here's the thing, the more we learn about dark matter, the more questions we uncover. Why does it refuse to interact with light? What strange particles make up its hidden form? And how does it sculpt the universe on scales so grand it defies everything we thought we knew? Today, we're diving deep into 25 of the most baffling, awe-inspiring mysteries surrounding these cosmic halos, each one a puzzle that could rewrite the rules of physics as we know them. From ghostly gravitational echoes to the eerie way dark matter seems to disappear in certain galaxies, we're about to explore the edges of human understanding where every answer leads to 10 new questions. This isn't just a story about science, it's a journey into the unknown, a detective story written across the cosmos itself, and you're invited to join the hunt. So let's peel back the veil of the universe together, because what we're about to uncover might just change how you see the night sky forever. The clues are out there, hidden in the darkness, and the truth, well, it's stranger than anything we've imagined. The first, and perhaps most baffling, mystery of dark matter halos is their invisibility. It sounds like something straight out of science fiction, a form of matter that dwarfs everything we can see, yet remains utterly hidden from our eyes, our telescopes, even our most advanced detectors. Think about that for a moment. Every star, every planet, every speck of interstellar dust we've ever observed makes up less than 20% of the universe's total matter. The rest, a ghostly, intangible substance that doesn't shine, doesn't reflect, doesn't absorb light in any way. So how do we even know it's there? The answer lies in gravity, the one and only way dark matter betrays its presence. Take galaxies, for example. They spin so fast that, according to the laws of physics, they should tear themselves apart. The visible matter alone doesn't have enough gravitational glue to hold them together, yet somehow they stay intact. There must be something more, something unseen exerting an enormous gravitational pull. And that's where dark matter halos come in, vast, diffuse spheres of this mysterious material enveloping galaxies, anchoring them with their invisible weight. One of the most stunning proofs comes from cosmic mirages known as gravitational lensing. When light from distant galaxies passes near massive objects, its path bends, distorting the images we see, almost like looking through a funhouse mirror. But here's the twist. Sometimes that distortion happens where there's nothing visible to cause it. The Bullet Cluster, a famous collision of two galaxy clusters, gave us one of the clearest snapshots of this phenomenon. The visible matter hot gas got stuck in the middle of the crash, while the real mass, revealed by its gravitational effects, sailed right through, leaving the gas behind. It was as if we were watching a ghost walk through a wall, dragging the universe along with it. This is the paradox at the heart of dark matter. We can map its influence with astonishing precision, tracing its gravitational fingerprints across the cosmos. Yet, despite decades of searching, we still don't know what it is. Does it consist of undiscovered particles, strange and alien to everything we've ever encountered? Or is it something even more exotic, defying our current understanding of physics altogether? Every time we think we're closing in on an answer, the universe seems to whisper, "Look deeper." The invisible giant is still hiding in plain sight. If dark matter is the universe's best-kept secret, then the missing baryons are its most glaring oversight. We've long known that ordinary matter, the stuff that makes up stars, planets, and even us, only accounts for a tiny fraction of the cosmos. But here's the shocker, even that small fraction doesn't add up. According to our most sophisticated simulations, there should be far more ordinary matter, or baryons, lurking in the vast halos surrounding galaxies. Yet when we look, we come up short. It's as if the universe misplaced an entire population of particles, and no one knows where they went. This isn't just a minor accounting error. The missing baryons represent a gaping hole in our understanding of cosmic structure. Think of it like balancing a checkbook, only to discover half the entries have vanished into thin air. Supercomputer models predict that these baryons should exist as diffuse, superheated gas within dark matter halos, too faint to see with traditional telescopes. But when astronomers scan the skies, the numbers don't match. Somewhere between prediction and observation, something is slipping through our fingers. One leading theory suggests these elusive baryons might be hiding in vast, thread-like structures called the warm-hot intergalactic medium, or WIM. Picture a cosmic spiderweb stretching between galaxies, filled with gas so hot it glows in X-rays, but so sparse it's nearly transparent. Detecting this ghostly web is like trying to spot a whisper in a hurricane. Even our most advanced instruments, like the Chandra X-ray Observatory, have only caught fleeting glimpses. Then there's the wild card, warm dark matter. Unlike its colder cousin, this hypothetical form of dark matter would consist of lighter, faster-moving particles, subtly altering how ordinary matter clusters around it. If warm dark matter exists, it could explain why some baryons seem to evaporate from halos, vanishing into the cosmic background. But this idea comes with its own headaches. Warm dark matter would also leave fingerprints on the formation of dwarf galaxies, fingerprints we haven't definitively found yet. And let's not forget the most radical possibility, exotic particles beyond our current physics. Could some unknown interaction be converting baryons into something entirely new? Theories like decaying dark matter or hidden dimensions flirt with this idea, suggesting that what we call missing might simply be masquerading as something else. The problem is, the more exotic the solution, the harder it is to test. What makes this mystery so tantalizing is its sheer audacity. Here we are, armed with equations and supercomputers, and yet a chunk of the universe's ordinary matter has seemingly ghosted us. Every time we think we've pinned it down, it slips away again, leaving behind more questions than answers. The missing baryons aren't just a cosmic oversight, they're a glaring reminder of how much we still don't understand about the dark scaffolding of the universe. And until we solve this puzzle, our map of reality will remain frustratingly incomplete. Dark matter halos should be perfect spheres, at least that's what our best theories predict. Picture a vast, invisible bubble encasing a galaxy, its gravity holding everything together in a symmetrical embrace. But the universe, as always, loves to defy expectations. When astronomers actually measure these halos, they don't find neat, round shapes. Instead, dark matter halos often appear squashed, elongated, or even warped into triaxial forms, like cosmic footballs tumbling through the void. So why the mismatch between theory and reality? The answer might rewrite our understanding of dark matter itself. The spherical halo idea comes from something called the Navarro-Frank-White profile, a mathematical model that's been the gold standard for decades. It assumes dark matter particles are cold, slow-moving, and gravitationally dominant, naturally settling into smooth, spherical distributions over time. And for a while, it worked beautifully, explaining the broad structure of galaxies and clusters. But as telescopes grew sharper, so did the contradictions. Take the Milky Way's halo. Instead of a perfect sphere, it's slightly flattened, as if an invisible hand pressed down on the poles. Even more baffling are halos around some dwarf galaxies, which seem stretched into lopsided triaxial shapes like a potato tumbling through space. This discrepancy throws fuel on an already fiery debate about galaxy rotation curves. For years, astronomers have noticed that stars on the outer edges of galaxies orbit way too fast for the visible matter alone to hold them. Dark matter was the elegant fix, but if halos aren't spherical, their gravitational pull would warp those orbits in ways we don't always see. Some galaxies, like the ultra-diffuse Dragonfly 44, spin so sluggishly they barely need any dark matter, while others, like the famously fast-spinning NGC 342, defy expectations entirely. These outliers force us to ask, is dark matter's behavior more complex than we thought? One radical possibility is that dark matter isn't cold at all. It could be warm, with lighter, faster particles that refuse to settle neatly into spherical halos. Or perhaps dark matter interacts with itself through some unknown force, creating internal turbulence that distorts its shape. There's even a fringe theory that dark matter halos aren't static but dynamic, their forms flickering and shifting over cosmic time. But here's the twist. What if the problem isn't dark matter but us? Our models rely on gravity alone, ignoring potential wild cards like magnetic fields or galactic collisions that could stretch halos into odd shapes. The Andromeda Galaxy, for instance, shows signs of a past cosmic crash, a violent merger that might have yanked its halo into a triaxial form. If that's true, then every flattened halo could be a fossil record of ancient chaos, a relic of universes past. The halo shape mystery cuts to the heart of cosmology. Are we missing a fundamental law or just misreading the clues? Every lopsided halo, every contradictory rotation curve, is a signpost pointing toward answers we haven't grasped yet. And until we do, the true shape of dark matter remains one of the universe's most stubborn enigmas, a cosmic riddle written in invisible ink. One of the most puzzling contradictions in modern cosmology doesn't come from the vast spirals of giant galaxies, but from their tiniest neighbors. Dwarf galaxies, these faint, scrappy collections of stars scattered around larger galaxies like cosmic fireflies, should be the perfect place to study dark matter. Their small size means dark matter should dominate their gravity, leaving clear fingerprints in how they move and behave. But when scientists compare real dwarf galaxies to supercomputer simulations, something doesn't add up. The simulations predict these galaxies should sit inside enormous, dense dark matter halos so massive they've been nicknamed too big to fail. Yet when we look at actual dwarfs, their halos are suspiciously lightweight, almost as if the dark matter has gone missing. This mismatch isn't just a minor glitch, it's a full-blown crisis for our understanding of dark matter's behavior. Take the Milky Way's satellite dwarfs like Draco or Ursa Minor. According to simulations, their dark matter halos should be so dense they'd form hundreds of visible stars. But instead, these galaxies are eerily dim with far fewer stars than expected. It's like expecting a bustling city and finding a ghost town. Even stranger, some ultra-diffuse galaxies like Antlia 2 have so few stars they're practically transparent, yet their dark matter halos are bizarrely sparse, defying every prediction. So where did the dark matter go? One provocative idea is that dark matter might not be as dark as we think. It could interact with itself through some unknown force, scattering particles like billiard balls and smoothing out halos into fluffier, less concentrated forms. This self-interacting dark matter theory would explain why dwarf halos seem underweight. Their particles could be bouncing off each other, redistributing mass until the halo puffs up like a cosmic souffle. There's even tantalizing evidence from galaxy cluster collisions, where dark matter appears to lag behind visible matter, as if it's feeling friction from unseen interactions. But not everyone's convinced. Alternative theories suggest that cosmic violence, exploding supernova or violent galactic tides, might have ripped dark matter away from these dwarfs, leaving them stranded in unnaturally thin halos. Others argue the problem isn't with dark matter at all, but with how we model galaxy formation. Maybe stars in dwarfs form less efficiently than we thought, or perhaps the simulations overestimate how much gas collapses into visible matter. Then there's the nuclear option. What if dark matter isn't a single type of particle, but a mix of different species, some heavy and slow, others light and fast? This mixed dark matter scenario could create halos with complex, layered structures, dense cores wrapped in wispy outskirts, matching the weird diversity of dwarf galaxies we observe. The too big to fail problem is more than just a technical headache. It's a direct challenge to our most fundamental assumptions about the invisible 85% of the universe. Every underweight dwarf galaxy is a clue, a piece of cosmic feedback whispering that we might be missing something profound. Whether the answer lies in self-interacting particles, overlooked astrophysics, or something even stranger, one thing's clear: dark matter isn't playing by the rules we wrote. And that's what makes this mystery so thrilling. The universe loves to surprise us, and these stubborn little galaxies are holding the next big revelation hostage until we crack their code. At the heart of every dark matter halo lies a fierce cosmic debate, one that pits the sharp, dense spikes predicted by theory against the soft, blurry centers we actually observe. This is the cusp-core controversy, a puzzle so stubborn it's forced scientists to question whether dark matter behaves the way we think it does. Simulations say halos should have cusps, regions where dark matter piles up in a steep, intense peak at the center, like a mountain with an impossibly sharp summit. But when astronomers study real galaxies, especially small, faint dwarfs, they find something entirely different: gentle, chord profiles where the dark matter's density flattens out, more like a rolling hill than a jagged cliff. The disconnect is so glaring it sparked a decades-long tug of war between theory and observation. Take the classic cold dark matter model, which assumes dark matter particles are slow-moving and collisionless. They pass right through each other like ghosts. Supercomputer simulations based on this idea, like the famous Millennium Run, consistently produce halos with those sharp cusps. Yet when scientists measure the motions of stars in dwarf galaxies like Fornax or Sculptor, the data screams otherwise. Stars orbiting near the center move way too slowly for a steep cusp to be present. Instead, their speed suggests the dark matter is spread out, dilute, almost as if something scooped out the halo's core. One radical explanation: dark matter might not be completely dark after all. If particles interact with each other, even weakly through forces beyond gravity, they could scatter and redistribute energy, smoothing out the central cusp into a core. Picture a crowded dance floor where particles occasionally bump shoulders, gradually shifting toward the edges until the center thins out. There's tantalizing evidence for this in some galaxies, like the ultra-diffuse NGC 1052, where the dark matter's distribution is so soft it's practically hollowed out. But here's where things get messy. Not all galaxies fit this pattern. Some, like the compact dwarf Segway 1, show hints of cuspy profiles, while others, like the sprawling Leo T, are textbook cores. The inconsistency has led to a zoo of competing theories. Maybe supernova explosions in small galaxies blast out gas and drag dark matter with them, puffing up the core. Or maybe the tug of a larger galaxy's tide strips dark matter from the center, leaving it oddly diffuse. There's even a wild card, fuzzy dark matter, made up of ultralight particles so wave-like they naturally smear out cusps into cores. The stakes couldn't be higher. If cores are real and cusps are wrong, it might mean dark matter is far more complex than a simple, sluggish particle. Every flattened core is a clue, a whisper that the universe's dominant substance might be playing by rules we haven't uncovered yet. And until we solve this riddle, our simulations, the very foundation of modern cosmology, are building galaxies on shaky ground. The cusp-core controversy isn't just academic nitpicking, it's a battle for the soul of dark matter itself, fought in the silent centers of the cosmos' faintest galaxies. Dark matter doesn't just lurk around galaxies, it weaves the very skeleton of the cosmos, an invisible architecture stretching across billions of light years. Picture the universe as a colossal spiderweb, its strands glistening with galaxies, and you're seeing the handiwork of dark matter halos. These halos aren't isolated islands, they're interconnected nodes in a vast filamentary network known as the cosmic web. Without them, the universe would be a shapeless void, a cosmic soup without structure. The cosmic web is dark matter's masterpiece. After the Big Bang, tiny quantum fluctuations seeded regions where dark matter began clumping together, drawing in gas and dust like cosmic magnets. Over eons, gravity amplified these clumps, sculpting them into halos, but the real magic happened in between. Thin, thread-like tendrils of dark matter linked halos together, forming rivers of invisible mass where galaxies would later flow. Today, we see this web etched across the sky. Galaxy clusters sit at the intersections of filaments, while lonely voids, millions of light years wide, stretch between them like empty rooms in an endless mansion. One of the most stunning confirmations of this web came from the Sloan Digital Sky Survey, which mapped millions of galaxies and revealed their eerie alignment along these filamentary highways. But here's the twist: the galaxies are just the visible icing on an invisible cake. The real structure, the scaffolding, is pure dark matter, detectable only by its gravitational grip. Simulations like the Illustris TNG project show these filaments in vivid detail, with halos glowing like pearls on a string, connected by dark matter's ghostly threads. Yet the cosmic web isn't static, it's a dynamic, ever-evolving tapestry. When two filaments collide, they funnel gas and dark matter into frenzied knots, birthing galaxy clusters. Elsewhere, filaments stretch and thin, draining matter from some regions and feeding others. This cosmic redistribution shapes everything from the tiniest dwarf galaxies to the largest superclusters, all orchestrated by dark matter's silent choreography. But the web holds mysteries of its own. Why do some filaments seem underdense, as if dark matter is avoiding them? And how do these threads remain so stable over cosmic time, resisting the pull of collapsing halos? Some theories suggest dark matter's inherent coldness. Its slow, sluggish motion helps maintain the web's delicate balance. Others speculate that unknown interactions between dark matter particles might subtly reinforce filaments like invisible glue. The cosmic web isn't just a backdrop, it's the universe's blueprint. Every galaxy, every cluster, every void exists because dark matter laid the groundwork first. And as we peer deeper into this hidden framework, we're not just mapping the cosmos, we're deciphering the rules of its construction. The filaments may be invisible, but their influence is written in the stars. Imagine our Milky Way not as a lonely island in the cosmos, but as the center of a bustling miniature empire surrounded by hundreds of tiny satellite galaxies, each tethered by invisible threads of dark matter. That's what supercomputer simulations insist should be there. But when astronomers peer into the night sky, they count only about 60 of these cosmic attendants. This glaring discrepancy, known as the missing satellites problem, has haunted astrophysics for decades. If our models of dark matter halos are correct, where are all those dwarf galaxies hiding? The roots of this puzzle trace back to the earliest computer simulations of cosmic structure formation. Programs like the Millennium Run or Via Lactea modeled how dark matter should clump together after the Big Bang, painting a universe where every massive galaxy like ours sits at the heart of a sprawling entourage, hundreds, even thousands of smaller satellite galaxies. These dwarfs would be the leftover crumbs from the Milky Way's formation, orbiting like moths around a street lamp. Yet when sky surveys like the Sloan Digital Sky Survey swept the heavens, they kept turning up far fewer satellites than predicted. It was as if someone had erased 3/4 of the Milky Way's expected retinue. One possible explanation, maybe we just haven't found them yet. Some of these missing satellites could be so faint, so star-poor, they're virtually invisible to current telescopes. Take the case of Segway 1, a dwarf galaxy discovered in 2006. It's so dim that for years it blended seamlessly into the background of the Milky Way's glow. Only by tracking the motion of its sparse stars could astronomers confirm its existence. There might be dozens more like it lurking in the shadows, waiting for next-generation instruments like the Vera Rubin Observatory to spot them. But what if the answer isn't just about visibility? Another theory points to the brutal environment around large galaxies. The Milky Way's gravity doesn't just gently shepherd its satellites, it devours them. Over billions of years, tidal forces shred dwarfs apart, dispersing their stars into vast, ghostly streams. We've already spotted remnants of these cannibalized galaxies, like the Sagittarius dwarf, currently being torn into a cosmic ribbon. If this destruction happens fast enough, it could explain why so few satellites remain today. Then there's the dark matter angle. If dark matter particles are warmer, lighter and faster moving than traditional, cold, dark matter models assume, they'd form fewer, fluffier small halos, naturally reducing the number of visible satellites. Or perhaps the earliest universe suppressed star formation in the tiniest halos, leaving them dark and nearly undetectable. Some simulations, like those incorporating fuzzy, dark matter composed of ultralight particles, show halos so diffuse they barely gather enough gas to spark a single star. But here's the twist: the missing satellites might not be missing at all. Recent observations suggest many could be hiding inside the Milky Way itself. When two galaxies merge, their satellite systems collide, scattering dwarfs into chaotic orbits that make them harder to track. The Gaia spacecraft has already spotted strange groups of stars moving in unison, ghosts of ancient satellite galaxies now dissolved into the Milky Way's halo. The deeper we dig, the clearer it becomes. This isn't just a census error. The satellite galaxy puzzle forces us to question the very nature of dark matter, the violence of galactic evolution, and the limits of our telescopes. Every undetected dwarf is a silent witness to the gaps in our cosmic story, and until we solve this mystery, we're left staring at a sky that refuses to match our expectations, a reminder that the universe always keeps a few cards hidden up its sleeve. Hidden in the depths of galaxy clusters, drifting like phantom ships, are some of the most perplexing structures in the cosmos: ultra-diffuse galaxies. These cosmic ghosts, like the now famous Dragonfly 44, stretch as wide as the Milky Way but glow with barely 1% of its starlight. They're so faint that until recently, they slipped right past our telescopes, masquerading as empty patches of sky. But the real shock came when astronomers measured their mass. Despite their ethereal appearance, these galaxies weigh as much as giant spirals, meaning they're packed with staggering amounts of dark matter, up to 99% of their total mass. Take Dragonfly 44, discovered in 2015 in the Coma cluster. At first glance, it seemed like a cosmic afterthought, a wispy smear of stars so sparse you could practically see right through it. But when researchers tracked the motions of its stars, they were stunned. Those few, lonely suns were whipping around at speeds that betrayed the presence of a dark matter halo rivaling our own Milky Ways. This shouldn't happen. According to conventional wisdom, galaxies with such feeble starlight should be lightweight, their dark matter halos barely substantial enough to hold them together. Yet here was Dragonfly 44, flaunting a gravitational grip hundreds of times stronger than its visible matter could explain. The mystery deepens when you consider how these galaxies survive at all. Most ultra-diffuse galaxies live in the brutal environments of galaxy clusters, places where gravitational tides and collisions should tear fragile structures apart. Somehow, these wispy giants endure, their dark matter halos acting like cosmic shock absorbers. One theory suggests their halos might be unusually puffy, spreading mass over vast volumes to resist disruption. Others propose these galaxies are failed giants, ancient relics that formed too early, their star formation stifled before they could grow bright, but the real head-scratcher. Some ultra-diffuse galaxies, like NGC 1052, appear to have almost no dark matter at all. It's as if the universe is playing a cruel joke, presenting two opposite extremes: galaxies drowning in dark matter and others bizarrely devoid of it. This stark contradiction threatens to upend our understanding of how dark matter and galaxies co-evolve. Could dark matter be more dynamic than we thought? Perhaps it's capable of being stripped away or concentrated by cosmic events we haven't yet imagined. Or maybe ultra-diffuse galaxies are the skeletons of violent pasts, their stars scattered by ancient collisions, leaving behind ghostly remnants. Every new discovery in this field feels like uncovering a lost chapter in the universe's history, written in ink we're only just learning to see. Where does a dark matter halo end? It's a question that sounds simple until you realize these invisible structures don't come with neat edges like planets or stars. Instead, they fade into the cosmic background like a whisper lost in the wind, their boundaries blurred by gravity's relentless pull. Unlike the crisp silhouette of a galaxy, dark matter halos have no clear-cut border. Their outer layers, what astronomers call the virial radius, are more like a statistical estimate than a physical wall, a zone where the halo's grip on matter weakens just enough to blend into the void. But here's the catch: even this fuzzy boundary isn't fixed. Halos are constantly under siege, their edges shredded by a phenomenon called tidal stripping. Picture two galaxies passing near each other, their dark matter halos stretching like taffy as gravity tugs them apart. The outer layers, less tightly bound, get ripped away in vast streams, cosmic fingerprints of an unseen battle. The Milky Way's own halo bears these scars, stellar streams like GD1, a ribbon of stars winding through our galaxy, are thought to be the debris of dwarf galaxies torn apart by these tidal forces, their dark matter stripped and scattered into the abyss. These collisions don't just erode halos, they redefine them. When halos merge, their outer edges become a chaotic frontier, a no-man's land where dark matter particles are stolen, exchanged, or flung into intergalactic space. The Andromeda Galaxy, for example, shows signs of a colossal collision in its past, its halo likely reshaped by ancient encounters that left behind invisible wakes. Simulations reveal these interactions in stunning detail. Halos don't just pass through each other like ghosts, they twist, warp, and leave behind faint echoes of their struggle. The real puzzle lies in mapping these phantom borders. Unlike stars or gas, dark matter leaves no light to trace its outermost reaches. Instead, astronomers rely on tracers, hypervelocity stars ejected from the galactic center, or the distorted paths of globular clusters, to probe the halo's fringes. Even then, the data is messy. Some studies suggest the Milky Way's halo might extend nearly 2 million light-years, far beyond previous estimates, while others argue tidal forces have whittled it down to a mere fraction of that. And then there's the intergalactic dark matter particles that never settled into halos at all, drifting in the vast spaces between galaxies like cosmic nomads. Could this lost dark matter be the key to understanding why halos seem to fade so gradually? Or does it hint at something stranger, that dark matter's influence isn't confined to halos but weaves through the entire universe in ways we're only beginning to grasp? The edges of dark matter halos aren't just a technicality. They're a front line in the struggle to understand how these invisible giants grow, interact, and evolve. Every torn stream, every stretched boundary, is a clue to the forces shaping the universe, forces we can't see, but whose handiwork is written in the silent dance of the cosmos. Deep in the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, an enigma so dense it warps space-time itself. But here's the cosmic twist: these monstrous voids don't exist in isolation. They're cradled within vast dark matter halos, their fates intertwined in a gravitational dance that raises one of the most tantalizing questions in astrophysics: which came first, the black hole or the halo? The conventional wisdom suggests halos acted as cosmic nurseries, their immense gravity wells funneling gas and dust into galactic centers until collapsing under their own weight and igniting black holes. Picture a dark matter halo as a colossal whirlpool, slowly dragging matter toward its core until a singularity blooms in the darkness. This idea gained traction when astronomers noticed an eerie correlation. The more massive a galaxy's dark matter halo, the larger its central black hole tends to be. The Milky Way's own Sagittarius, a star weighing in at 4 million solar masses, seems perfectly matched to its halo's grand scale. But not all observations fit this neat narrative. Some of the universe's earliest supermassive black holes, like the behemoth-powering quasar 618, which existed when the cosmos was barely 1 billion years old, are too big, too fast. How could they have grown so massive so quickly unless they were already there, lurking in the primordial darkness before their halos fully formed? This paradox has led to a radical rethinking. Perhaps black holes came first, acting as gravitational anchors around which dark matter halos assembled. One provocative theory suggests these early giants might have sprouted from direct collapse black holes, primordial seeds born not from stars but from the violent collapse of vast gas clouds in the infant universe. These titanic seeds, thousands of times more massive than typical stellar black holes, would have provided the gravitational muscle to pull in dark matter, sculpting halos around themselves like cosmic sculptures molding their own foundations. Then there's the wild card of feedback. Black holes aren't passive monsters, they're chaotic engines blasting out torrents of energy as they devour matter. These outbursts can heat surrounding gas, stifling star formation and effectively putting a brake on halo growth. In galaxies like M87, where the central black hole spews a jet of plasma thousands of light-years long, this feedback may have reshaped the entire dark matter distribution, carving out cavities in the halo like a spoon through cosmic custard. But the plot thickens when you consider wandering black holes, rogues ejected from their galactic cores during violent mergers. These nomads, stripped of their stellar surroundings, might still carry vestiges of their original halos like invisible cloaks. If so, they could be the universe's dark matter probes, their paths betraying the presence of otherwise undetectable halo fragments. The relationship between black holes and halos isn't just academic. It's a window into how structures emerge in the cosmos, how chaos begets order, and how the universe's most violent objects might quietly orchestrate the growth of everything around them. Every supermassive black hole is a time capsule, holding clues to whether dark matter halos are architects or aftermath, a cosmic chicken and egg riddle written in gravity's own hand. To understand how dark matter halos came to be, we must rewind the cosmic clock nearly 13.8 billion years, back to a time when the universe was little more than a seething cauldron of energy. In those first fleeting moments after the Big Bang, the cosmos was a near-perfect soup of particles, so uniform that you could barely tell one region from another. Yet hidden within that apparent sameness were the faintest ripples, quantum fluctuations so tiny they'd fit inside a trillionth of an atom. These minuscule wrinkles, stretched to cosmic proportions during a period called inflation, became the seeds of everything we see today. Inflation, the universe's explosive growth spurt, magnified those quantum whispers into grand density variations. Picture a balloon inflating so rapidly that tiny ink dots on its surface stretch into vast, sprawling patterns. That's what happened to those primordial fluctuations. They became the blueprint for dark matter's cosmic architecture. As the universe expanded and cooled, dark matter, still mysterious in its composition but governed by gravity, began clumping around these slightly denser regions. The overdense areas acted like gravitational magnets, pulling in more and more dark matter over time, while the underdense zones emptied out, creating the first cosmic voids. But here's where it gets fascinating. Dark matter halos didn't just pop into existence fully formed, they grew hierarchically like snowballs rolling downhill. Tiny clumps merged into larger ones which collided and combined again, building up structures in a process aptly named bottom-up formation. The earliest halos, no heavier than a single Earth mass, likely appeared within the universe's first million years, long before stars or galaxies even had a chance to ignite. Over eons, these minuscule halos aggregated into the colossal structures we see today, their invisible gravitational scaffolding shaping the galaxies within them. The smoking gun for this theory, the cosmic microwave background, the afterglow of the Big Bang. WMAP and Planck satellite observations reveal a nearly identical pattern of temperature fluctuations in this ancient light, mirroring the distribution of dark matter halos we infer from modern galaxy surveys. It's as if we're staring at the universe's baby photos, seeing the very ripples that would one day dictate where galaxies cluster and where voids stretch empty. Yet mysteries linger. Why did some regions collapse into halos faster than others? Could dark matter's hypothetical interactions beyond gravity have altered this growth? And what role did the universe's earliest black holes play in seeding these structures? The birth of halos isn't just a historical curiosity, it's the foundation of cosmic evolution, a process that continues to shape the universe in ways we're only beginning to decode. What happens to dark matter halos in the far future? Do they dissolve into the void like cosmic smoke, collide and merge into something greater, or stand untouched as the universe grows cold and dark around them? The fate of these invisible giants isn't just academic, it's a window into the ultimate destiny of the cosmos itself. Take evaporation. Some theories suggest dark matter might not be truly eternal. If it consists of weakly interacting massive particles, or WIMP, there's a slim chance these particles could decay over unimaginable timescales, transforming into lighter particles or pure energy. Picture a halo not as a permanent structure, but as a sandcastle slowly crumbling under an endless tide. The process would be agonizingly slow, perhaps taking hundreds of trillions of years. But if it happens, halos could fade into nothingness, leaving galaxies unmoored. Yet decay isn't the only path. In a universe where dark matter is stable, halos might face a different destiny: collisions. Right now, we see this play out in galaxy clusters like the Bullet Cluster, where two halos have crashed through one another like ghostly ships passing in the night. Over eons, these mergers could become the norm. As gravity pulls galaxies closer, their halos will smash together, their dark matter particles threading through each other like two hands clasping in the dark. Some simulations predict a future where all halos in a local group eventually blend into one monstrous superhalo, a vast invisible web binding the wreckage of galaxies together. But there's a wilder possibility. If dark matter interacts with itself not just through gravity but through some unknown force, halos could behave more like fluids, swirling and mixing in ways we can't yet predict. Imagine two halos merging not with a whisper but with a splash, their dark matter particles ricocheting off each other like billiard balls, reshaping their structures entirely. This could leave behind halos that are lumpy, asymmetrical, or even riddled with voids, a far cry from the smooth, spherical giants we model today. Then there's the grandest timeline of all, the heat death of the universe. As expansion accelerates and galaxies vanish beyond the cosmic horizon, halos could be the last structures standing, their gravitational bonds outlasting stars, black holes, even time itself. In this bleak future, dark matter halos might float in absolute isolation, the sole remnants of a universe that once teemed with light and life. The ultimate fate of halos hinges on questions we're still grappling with. Is dark matter truly immutable, or does it erode? Does it interact in ways beyond gravity, or is it as silent and passive as it seems? Every observation, from the faintest dwarf galaxy to the largest cosmic web filament, is a clue to how this story ends. And while we may never witness the final act, the clues we uncover now will echo across eternity. One of the most unexpected discoveries about dark matter halos is that some of them spin slowly, silently, like vast cosmic whirlpools hidden in the void. This rotation defies the classic image of halos as static, featureless blobs of invisible matter. Instead, it suggests their dynamic structures with their own internal motion, sculpting the galaxies within them in ways we're only beginning to understand. Take spiral galaxies like the Milky Way. Their iconic arms, brimming with young stars and glowing gas, trace out a delicate pinwheel pattern, one that only makes sense if the entire system, dark matter halo included, is rotating in sync. Observations show our galaxy's halo completes a full turn roughly every billion years, dragging stars and gas along with it like leaves caught in a gentle current. This shared rotation is no accident. As the halo spun in the early universe, its angular momentum shaped the collapsing gas at its center, imprinting that spin onto the fledgling galaxy. But not all halos play by these rules. Elliptical galaxies, those smooth, football-shaped collections of ancient stars, often reside in halos that show little to no rotation. Instead, their stars orbit chaotically, buzzing around the center like disoriented bees. The difference comes down to violence. While spiral galaxies form gradually from gently spinning gas clouds, ellipticals are thought to be the products of catastrophic mergers, where multiple galaxies smash together, their halos colliding in a gravitational frenzy that scrambles any orderly rotation. The result, a halo that's more like a stirred-up beehive than a spinning top. The real intrigue lies in the outliers' halos that should spin but don't, or ones rotating far faster than expected. The ultra-diffuse galaxy NGC 1052, for instance, barely spins at all despite its sprawling size. Meanwhile, some dwarf galaxies whirl at breakneck speeds, their halos seemingly cranked up to 11. These oddballs hint at a deeper complexity in how halos acquire their spin. One possibility is that cosmic filaments, those vast rivers of dark matter weaving through the universe, act like invisible conveyor belts, transferring angular momentum to halos as they form. Halos born along fast-moving filaments might inherit a fierce spin, while those forming in quieter cosmic backwaters could end up still. There's also the wild card of mergers. When two halos collide at just the right angle, their combined rotation could amplify or cancel out, like two tops smacking into each other mid-spin. But the biggest question remains, does a halo's rotation dictate a galaxy's fate, or is it the other way around? For spiral galaxies, the answer seems clear: their halo's spin sets the stage for everything that follows. Yet ellipticals complicate the picture, proving that even the most orderly rotations can be erased by cosmic chaos. Every spinning halo is a fossil record of the forces that shaped it, a silent witness to the universe's endless dance of creation and destruction. At first glance, dark matter and dark energy couldn't seem more different. One is the invisible glue holding galaxies together. The other is the mysterious force ripping the universe apart at ever-increasing speeds. Yet here's the cosmic curveball. Today, their energy densities are almost eerily similar, not just in the same ballpark, but within a factor of 2 or 3 of each other. This bizarre near-equality, known as the cosmic coincidence problem, is one of the most perplexing riddles in modern cosmology. Why now? Why, after 13.8 billion years of expansion, do these two enigmatic forces happen to match in strength just as humans evolved to notice it? To appreciate how strange this is, rewind the cosmic tape. In the universe's youth, dark matter utterly dominated. Its gravitational pull sculpted galaxies and clusters, while dark energy, far weaker in comparison, was little more than a whisper in the void. Fast forward to the distant future, and the tables will turn completely. Dark energy's repulsive force will accelerate expansion until galaxies vanish beyond the horizon, leaving dark matter's halos isolated and irrelevant. But today, we're caught in a fleeting sliver of cosmic time where these two giants briefly balance each other like two titans pausing mid-tug of war. This coincidence is so jarring that some physicists suspect it's no accident. There might be a hidden link between the two. One provocative idea, called quintessence, suggests dark energy isn't constant but evolves over time, its strength tied to the density of dark matter. Picture a cosmic seesaw. As dark matter dilutes with expansion, dark energy's influence grows, maintaining an uneasy equilibrium. Theories like coupled dark energy take this further, proposing dark matter and dark energy directly interact, exchanging energy in ways that keep their densities roughly aligned. But not everyone buys into these elegant solutions. Critics argue the apparent balance might just be a fluke, a random roll of the cosmic dice that happens to favor our particular era. After all, if the universe's expansion rate had been slightly different, we wouldn't exist to ponder the question. This anthropic reasoning frames the coincidence as a selection effect. We observe this balance because it's the only one that allows galaxies and life to form. Then there's the nuclear option. Maybe our entire understanding of these components is flawed. What if dark matter and dark energy aren't separate entities at all, but different faces of the same underlying phenomenon? Theories like modified gravity attempt to unify them under a single framework, rewriting Einstein's equations to erase the need for both. But these proposals struggle to explain phenomena like the bullet cluster, where dark matter's gravitational fingerprint is clearly visible, separate from ordinary matter. The dark matter-dark energy tango isn't just academic nitpicking. It cuts to the heart of why our universe looks the way it does, and whether its apparent fine-tuning hints at deeper laws we've yet to uncover. Every observation, from supernova surveys to the cosmic microwave background, is a step toward untangling this dance. And until we solve it, we're left staring at a cosmic scale that for now remains mysteriously balanced. Is dark matter cold, warm, or hot? It's not a question about actual temperature. These labels describe how fast the invisible particles move, and the answer could reshape everything we know about cosmic structure. The debate over dark matter's thermal personality is one of the fiercest in modern physics, splitting scientists into rival camps with starkly different visions of the universe. Start with the reigning champion, cold dark matter. This model assumes particles are sluggish and heavy, lumbering through space like cosmic tortoises. Their slow speed lets them clump easily, forming the dense, small-scale halos we see in simulations perfect for seeding galaxies. WIMP, or weakly interacting massive particles, are the poster child here, theoretical heavyweights that barely interact with normal matter except through gravity. For decades, this framework neatly explained cosmic structures from galaxy clusters to the cosmic web, but cracks emerged. Why do simulations overpredict dwarf galaxies? Why are some halo cores strangely fluffy? The cold model struggles with these quirks, leaving room for challengers. Enter warm dark matter, the Goldilocks option. These particles are lighter and zippier, moving fast enough to smooth out small-scale clumps while still forming large halos. Think of them as cosmic foxes, quick, clever, avoiding dense traps. Sterile neutrinos, hypothetical cousins to the ghostly neutrinos we know, fit this profile. They'd leave a universe with fewer dwarf galaxies and softer halo cores, potentially solving the too big to fail and cusp-core problems in one swoop. There's even tantalizing evidence from the Lyman alpha forest patterns in distant quasar light that hint at warm dark matter's smoothing effect on ancient gas clouds. Then there's the underdog, hot dark matter, particles like regular neutrinos blazing through space at near light speed would resist clumping altogether, creating halos only on supergalactic scales. The problem: this model can't explain how galaxies formed so early. If dark matter were purely hot, the universe would be a sea of featureless plasma, with no stars or galaxies until far later. Yet hybrids exist. What if dark matter is a mix, some particles cold, some warm, each carving structures at different scales like a cosmic tag team? The hunt for answers isn't just theoretical. Underground labs like LUX Zeppelin scour for WIMP collisions in vats of liquid xenon. Space telescopes search for X-ray signatures of decaying sterile neutrinos. Even tabletop experiments hunt for actions ultralight particles so wispy they behave more like waves than matter. Each candidate paints a different future for cosmology. WIMP would mean halos are dense and layered. Actions might create halos that ripple like ponds. Sterile neutrinos could leave halos pockmarked with tiny voids. What's at stake? The very blueprint of the universe. Cold dark matter builds galaxies from the ground up. Warm versions might erase small structures entirely. And if dark matter's nature changes over time, say, particles decaying or interacting halos could be evolving under our noses. The temperature debate isn't academic. It's a battle for the soul of cosmic structure, where every new observation could tilt the scales. Until we detect these particles directly, the universe's hidden architects remain shadowy figures. Their fingerprints everywhere, their faces unseen. Dark matter halos aren't the smooth, featureless spheres we once imagined. They're cosmic Swiss cheese, riddled with clumps and smaller subhalos, like invisible islands floating within an even darker sea. These substructures are the fingerprints of the universe's violent past, remnants of smaller halos swallowed whole during galactic collisions. And they're not just cosmic trivia. They're reshaping our understanding of how galaxies evolve, merge, and even tear each other apart. Picture a halo as a vast, invisible metropolis. The main city might be the central hub, the massive dark matter envelope anchoring a galaxy like the Milky Way. But scattered throughout are smaller neighborhoods, subhalos that once belonged to other galaxies, now orbiting like silent satellites. Some of these substructures are massive enough to drag their own retinue of stars along, creating the dwarf galaxies we see today. Others are too faint to host any stars at all, lurking in the darkness like ghosts of failed galaxies. The sheer number is staggering. Simulations suggest our Milky Way's halo could harbor thousands of these subhalos, a hidden archipelago waiting to be mapped. But here's where it gets wild. When galaxies merge, their halos don't just blend smoothly, they leave behind scars. Subhalos can be ripped apart by tidal forces, their dark matter stretched into long, flowing rivers called tidal streams. We've spotted these streams winding through our own galaxy, like the Sagittarius Stream, a ribbon of stars torn from a cannibalized dwarf galaxy. These cosmic fingerprints are more than just pretty relics, they're forensic evidence, telling us how the Milky Way grew by devouring its neighbors. The real puzzle: some subhalos seem to be missing. Cold dark matter simulations predict far more substructure than we observe, especially around dwarf galaxies. It's as if the universe hit the delete button on a chunk of these clumps. One explanation could be that star formation in the tiniest subhalos was snuffed out early, leaving them too dim to detect. Or perhaps dark matter interacts with itself, smoothing out these smaller clumps over time. There's even a radical idea that warm dark matter, lighter, faster-moving particles, could naturally suppress small-scale substructure, solving the discrepancy in one swoop. Then there's the role of subhalos in galactic collisions. When two galaxies merge, their halos don't just pass through each other like phantoms. Subhalos can act like gravitational wrecking balls, stirring up stars, disrupting orbits, and even triggering bursts of star formation. The Milky Way's upcoming collision with Andromeda won't just be a dance of stars. It'll be a chaos of subhalos slamming through each other, reshaping both galaxies in ways we're only beginning to model. The clumpy nature of halos forces us to rethink the very nature of dark matter. Are these substructures proof of WIMP actions or something even stranger? Do they hold the key to why some galaxies look the way they do? every subhalo, every tidal stream is a piece of a puzzle we're still assembling, a reminder that even in the darkness, the universe is anything but smooth. We often think of dark matter halos as immutable cosmic scaffolding, silent giants that shape galaxies but remain untouched by them. But what if the opposite is also true? What if the ordinary matter within galaxies, stars, gas, and the furious energy they unleash could reach back and reshape the halos themselves? This two-way street, known as the feedback loop, is one of the most dynamic mysteries in modern astrophysics, revealing a universe where dark and light matter don't just coexist but actively dance. Picture a supernova, a star's catastrophic death blast. As the shockwave rips through a galaxy, it doesn't just light up the cosmos, it punches a hole in the surrounding dark matter halo, heating and displacing particles like a cosmic bulldozer. Multiply this by billions of stars, and suddenly, halos aren't passive containers, they're malleable. They're structures sculpted by the very galaxies they birth. Astronomers call this baryonic feedback, and its effects are written across the universe. Take dwarf galaxies. Their dark matter halos are often fluffier than simulations predict, with cores that seem scooped out. The culprit, generations of supernova, their cumulative explosions puffing up the halo like a souffle, counteracting gravity's pull. But stars aren't the only players. At the heart of many galaxies, supermassive black holes lurk like dormant dragons until they awaken. When these monsters feed, they unleash jets of plasma moving at nearly light speed, carving cavities in the surrounding gas and dark matter alike. The galaxy M87 offers a stunning example. Its black hole's jet stretches for thousands of light years, a disruptor so powerful it's likely reshaped the entire halo's inner structure. These active galactic nuclei, or AN, don't just light up the cosmos, they're cosmic sculptors, their fury echoing through the invisible dark matter scaffold. The feedback loop gets even wilder when galaxies collide. During a merger, bursts of star formation and AGN activity can inject so much energy into the halo that it temporarily puffs up, altering how future stars form. Some simulations suggest this might explain why certain massive galaxies stop forming stars entirely. Their halos, stirred into chaos, prevent new gas from cooling and collapsing. It's a cosmic irony. The very processes that build galaxies can also shut them down. Yet not all feedback is destructive. In quieter corners of the universe, gentle streams of gas might cool and settle back into halos, replenishing what was lost. This balance between heating and cooling, between chaos and order, could be the key to why halos look the way they do. Without feedback, halos would be denser, sharper, more monolithic, but the universe prefers complexity, a delicate negotiation between darkness and light. The deeper we look, the clearer it becomes. Dark matter halos aren't just backdrops. They're living, breathing structures, shaped as much by the galaxies within them as they shape those galaxies in return. Every supernova, every jet, every collision leaves its mark on the invisible fabric of the cosmos. And in that feedback loop, we're witnessing something profound, a universe where nothing, not even the darkness, exists in isolation. In the depths of the Virgo cluster, astronomers stumbled upon something that shouldn't exist, a cosmic ghost named Virgo 21. This bizarre structure has all the gravitational heft of a galaxy, with enough dark matter to hold billions of stars, yet it's almost completely empty. No glittering spirals, no glowing gas clouds, just an invisible halo floating silently in the void. It's as if someone took a galaxy and erased everything but its shadow. Virgo 21 isn't just an oddity, it's a direct challenge to our understanding of how galaxies form. According to conventional wisdom, dark matter halos are supposed to be the gravitational traps that pull in gas, compress it into stars, and light up the cosmos. So how could a halo this massive remain barren? One possibility is that it's a galactic stillbirth, a halo that somehow missed its chance to gather gas, leaving it forever dark. In the early universe, fierce ultraviolet radiation from the first stars might have sterilized certain regions, preventing gas from cooling and collapsing. Virgo Heat 21 could be a fossil from that era, a relic of a time when the universe was too hostile for stars to ignite. But there's a wilder explanation. Pure dark matter galaxies might be lurking everywhere, invisible to our telescopes. Simulations suggest thousands of these dark halos could orbit the Milky Way alone, too faint to detect unless they pass in front of something brighter. In 2020, the Dragonfly telescope spotted another candidate, an ultra-diffuse blob called NGC 1052, which appeared to have almost no stars at all. Yet its gravity betrayed it, revealing a dark matter halo nearly as massive as the Milky Way's. The real shock came when researchers realized these dark halos might not be empty by accident. They could be designed that way. Some theories suggest certain types of dark matter particles might repel gas, actively preventing star formation. Others propose that violent galactic encounters could strip halos of their gas, leaving behind naked skeletons of dark matter. The Antlia II dwarf galaxy, for instance, seems to have had its stars torn away by the Milky Way's tides, leaving only a wispy dark matter remnant behind. Then there's the spine-tingling prospect that these dark halos aren't anomalies at all, they're the norm. For every luminous galaxy we see, there could be dozens of invisible counterparts, a hidden population of ghosts silently shaping the cosmos. If that's true, our census of the universe is missing an entire class of objects, their presence only betrayed by the way they bend light or tug on their visible neighbors. The existence of pure dark matter halos forces us to confront a humbling truth. The universe might be far stranger than our models predict. Every time we think we've mapped the limits of cosmic structure, we find another shadow in the dark, another reminder that the universe keeps its deepest secrets well hidden. If dark matter halos are truly filled with invisible particles, there's a tantalizing possibility. They might betray their presence not through gravity alone, but through faint whispers of light. This is the premise behind indirect detection, the hunt for secondary signals like gamma rays or neutrinos, produced when dark matter particles annihilate or decay within halos. It's like listening for the echo of a shadow, searching for traces of something that refuses to be seen. One of the most compelling places to look is the heart of our own galaxy. The Milky Way's central halo should be a dark matter hotspot, its dense core potentially teeming with particles colliding and annihilating in bursts of high-energy radiation. The Fermi Gamma Ray Space Telescope has spent over a decade scanning this region, and in 2015 it spotted something peculiar, an excess of gamma rays emanating from the galactic center, precisely where dark matter models predicted they might appear. The signal, dubbed the galactic center excess, didn't match known astrophysical sources like pulsars or cosmic rays. For a brief, thrilling moment, it seemed like we might be staring at dark matter's smoking gun. But the cosmos is rarely so accommodating. Skeptics soon pointed out that the excess could also come from a population of undiscovered millisecond pulsars, ancient, rapidly spinning neutron stars too faint to detect individually. The debate rages on, with some analyses claiming the signal's distribution matches dark matter's expected profile, while others argue it's too clumpy to fit. The truth remains elusive, buried under layers of cosmic noise and competing interpretations. Beyond gamma rays, there's another ghostly messenger, neutrinos. These nearly massless particles, born in the hearts of stars and supernova, could also arise from dark matter annihilations. IceCube, the neutrino observatory buried in Antarctic ice, has scoured the skies for these elusive signals, particularly from massive halos like those around the Andromeda Galaxy or galaxy clusters. So far, the results are ambiguous, no definitive dark matter fingerprint, but enough tantalizing anomalies to keep physicists glued to their monitors. The challenges are staggering. Distinguishing dark matter's signal from astrophysical background is like picking out a single voice in a roaring stadium. Even the most promising hints, like Fermi's gamma-ray excess, could vanish under closer scrutiny. Yet the stakes are too high to quit. A confirmed detection wouldn't just prove dark matter exists, it would reveal its nature, mass, and interactions, unlocking the first real clues about the universe's hidden architecture. Indirect detection is a game of patience and precision, where every flicker of light or ripple in a detector could be the breakthrough or another dead end. But as long as dark matter halos loom in the cosmic dark, we'll keep listening for their echoes, hoping one will finally speak its name. What if everything we think we know about dark matter halos is just a shadow, a three-dimensional projection of something far stranger happening in higher dimensions? This mind-bending possibility, known as the holographic dark matter theory, suggests that halos might not be clumps of invisible particles at all, but cosmic mirages emerging from the edges of space-time itself. Imagine a black hole's event horizon, where information gets scrambled and encoded like pixels on a cosmic screen. Now stretch that idea across the entire universe. According to holographic principles, our three-dimensional reality, including dark matter's gravitational grip, could be the projected image of quantum data written on a distant, two-dimensional surface we'll never see. The roots of this idea trace back to string theory, where physicists grapple with the notion that gravity might be fundamentally weaker than other forces because it's leaking into higher dimensions. In this framework, dark matter's influence could be a side effect, a gravitational echo of interactions happening in dimensions beyond our perception. Picture a flashlight shining against a wall. The halo of light you see isn't the source, just a distorted projection. Similarly, dark matter halos might be the three-dimensional shadows of higher dimensional objects warping spacetime in ways we interpret as invisible mass. One startling prediction of holographic models is that halos should exhibit fractal-like patterns, their density fluctuating in precise mathematical rhythms. Intriguingly, some observations of galactic rotation curves do show subtle, wave-like deviations from classical predictions, as if the universe is whispering in geometries we're only beginning to decode. The European Space Agency's Gaia mission has even spotted strange, synchronized motions among stars in the Milky Way's outskirts, movements that could hint at a deeper, holographic order governing dark matter's distribution. But the theory faces fierce skeptics. If dark matter is just a projection, why do halos behave so convincingly like clumps of physical particles in simulations? Critics argue that holographic models struggle to explain the bullet cluster, where dark matter's gravitational lensing clearly separates from visible matter, a feat that seems to demand tangible mass. Proponents counter that even projections can carry effective gravity in higher dimensional frameworks, bending light through spacetime's geometry rather than particle interactions. The most radical twist, holographic dark matter might not even be matter at all, but a kind of cosmic glitch, a mismatch between how we perceive dimensionality and how the universe actually works. Think of a video game rendering only what the player sees to save processing power. What if dark matter is the universe's way of rendering gravitational effects it can't fully manifest in three dimensions? It's a dizzying thought that the halos we've mapped so meticulously could be optical illusions on a scale too vast to comprehend. Whether this theory holds up or collapses under scrutiny, it forces us to confront a humbling truth. Dark matter's enigma might not be about missing particles, but missing dimensions. Every unexplained halo quirk, every anomalous gravitational lens, could be a breadcrumb trail leading beyond the edges of our dimensional map. And if that's true, then the real mystery isn't just what dark matter is, it's where, or perhaps how, it truly exists. Deep in the cosmic dawn, when the universe was a mere infant, dark matter halos may have birthed objects so bizarre they defy modern astrophysics objects called dark stars. Unlike the blazing suns we know today, these theoretical giants wouldn't shine from nuclear fusion. Instead, they'd glow faintly from the annihilation of dark matter particles trapped in their cores. Picture a star not of fire but of shadow, fueled by the very substance we're still struggling to detect. If they exist, these primordial monsters could be time capsules, preserving secrets about dark matter's nature from a time before ordinary stars had even ignited. The math behind dark stars is as elegant as it is mind-bending. In the early universe, dark matter halos were smaller and denser, acting as gravitational traps for both dark matter and hydrogen gas. As particles collided and annihilated in these tight spaces, they'd release heat enough to prevent the gas from collapsing into conventional stars, but not enough to trigger fusion. The result, a vast, puffy behemoth, hundreds of times wider than our solar system, radiating a dim, eerie light powered purely by dark matter's hidden energy. Some models suggest these stars could have grown to millions of solar masses, dwarfing anything in the modern cosmos. This is where the James Webb Space Telescope becomes our time machine. Designed to peer back to the universe's first billion years, Webb might already have spotted these shadowy giants without realizing it. In 2023, astronomers were stunned when Webb detected galaxies that seemed too large, too bright, too soon after the Big Bang. But what if some of those galaxies are actually solitary dark stars masquerading as clusters? Their extended, diffuse glow could mimic early galaxies in certain wavelengths, while their unusual spectra, lacking the heavy elements forged in supernova, might betray their true identity. The implications are staggering. If dark stars are real, they'd act like cosmic Rosetta Stones, encoding clues about dark matter's interactions, mass, and even its role in jump-starting galaxy formation. Their sheer size would create gravitational lenses, bending light in ways that could help us map the distribution of dark matter in the infant universe. And if they eventually collapsed into supermassive black holes, skipping the star phase entirely, they might explain how black holes grew so enormous so quickly in the cosmic dawn. But the hunt is fraught with cosmic red herrings. Distinguishing a dark star from an early galaxy requires painstaking analysis of light curves and chemical fingerprints. Even Webb's razor-sharp vision might struggle to spot the telltale signs amid the noise of the early universe. Yet the payoff would be worth it. Confirmation of dark stars wouldn't just solve one mystery, it would crack open the entire puzzle of how dark matter shaped the cosmos from its very first breaths. Every anomalous glow, every too early giant in Webb's deep field images could be a whisper from the darkness waiting to be decoded. For all the dark matter halos we've mapped, those colossal, galaxy-cradling giants, there might be an even weirder population lurking in the cosmic shadows, ghost halos. These are the universe's abandoned construction sites, halos so faint and diffuse they never gathered enough gas to spark a single star. Picture a dark matter halo stretched thin, its gravitational pull too weak to trap the cosmic debris needed to build a galaxy. No stars, no gas, just a whisper of mass drifting unseen through the void. If they exist, these phantoms could be the missing link in one of cosmology's stickiest puzzles: why the cosmic web's filaments sometimes look emptier than they should. The evidence for ghost halos comes from the glaring mismatch between theory and observation. Supercomputer simulations like Illustris TNG predict a universe teeming with small halos, far more than the number of visible galaxies we've found. Some of this gap is explained by the too big to fail problem dwarf galaxies that should exist but don't. But another piece might be hiding in these ghost halos, structures so tenuous they slip past our telescopes entirely. They're the cosmic equivalent of a faint breath on a cold night. You know it's there, but it's nearly impossible to catch. So how do you detect something invisible even by dark matter standards? One clue lies in the cosmic web skeleton. Dark matter filaments those vast, thread-like rivers of mass connecting galaxy clusters. should be fringed with tiny halos like dew clinging to a spider web. But some filaments appear strangely sparse, as if chunks of their dark matter have gone AWOL. Ghost halos could be the culprits, their diffuse forms blending into the background like cosmic static. There's another tantalizing possibility. These halos might not be entirely dark. Some could harbor failed galaxies, pockets of gas too faint to form stars but still detectable through ultra-sensitive radio telescopes. The ALMA array in Chile, for example, has spotted clouds of molecular hydrogen floating unanchored to any galaxy. Could these be the last gasp of gas in a ghost halo's grip? Or perhaps these halos are home to rogue planets, black holes, or other dark objects ejected during galactic collisions, their presence only betrayed by microlensing events, brief flickers as they pass in front of distant stars. The most mind-bending twist, ghost halos might not be passive at all. If dark matter has even a slight ability to interact with itself, these halos could evolve over time, merging, stretching, or even dissolving into the cosmic background. Simulations of fuzzy, dark matter made up of ultralight, wave-like particles show halos that flicker in and out of existence, their boundaries never quite solid. In such a universe, ghost halos wouldn't just be leftovers. They'd be dynamic, ever-changing entities fading in and out like ripples on a pond. The hunt for these phantoms isn't just academic. If ghost halos are real, they'd force us to rethink how structures grow in the cosmos. Maybe the universe's first halos were inherently fragile, collapsing before they could shine. Or maybe dark matter's nature makes certain halos perpetually infertile, destined to wander the cosmic web as eternal spectral relics. Every unexplained gap in the filaments, every odd distortion in gravitational lensing, could be a clue pointing to these hidden giants, halos so ghostly, they've rewritten the rules of existence without us even noticing. The fabric of dark matter halos might be stitched together by forces we can barely comprehend, not just gravity as we know it, but something far stranger lurking at the quantum scale. Imagine the invisible scaffolding of the universe not as a smooth, continuous mass, but as a seething quantum foam, where microscopic black holes flicker in and out of existence, or where space-time itself trembles with fluctuations smaller than an atom. This isn't science fiction, it's the frontier of quantum gravity, and it could rewrite everything we think we know about halos. Take the idea of primordial black holes, theorized to have formed in the chaotic first moments after the Big Bang. These tiny, dense relics, some no heavier than an asteroid but as small as a proton, could be woven into the very structure of dark matter halos. If they exist, their combined gravity might explain why halos appear more clumpy than simulations predict, their mass distributed not smoothly but in an intricate quantum tapestry. Some researchers even suggest these black holes could be the dark matter itself, their collective weight anchoring galaxies without the need for exotic particles. The catch: finding them. A single primordial black hole drifting through our solar system might betray its presence by bending starlight or emitting a faint burst of Hawking radiation, a whisper of heat as it evaporates into nothingness. Then there's space-time itself. According to quantum mechanics, the vacuum of space isn't empty, it's a turbulent sea of virtual particles popping in and out of existence. These quantum fluctuations, infinitesimal as they are, might leave imprints on cosmic scales. Picture a dark matter halo not as a static object, but as a dynamic quantum field, its density rippling with fluctuations that subtly alter its gravitational pull. In certain models, these ripples could amplify in regions where dark matter is densest, creating unexpected hotspots within halos, places where gravity behaves just slightly differently than our equations predict. The most radical theories go even further, suggesting that dark matter's quantum nature might blur the line between particle and wave. If dark matter consists of ultralight actions, particles so wispy they behave more like waves than matter, their quantum interference patterns could sculpt halos into intricate, fluctuating shapes. These fuzzy halos wouldn't have sharp edges or smooth profiles, but undulating, wave-like boundaries, constantly shifting on scales we've yet to observe. Some astronomers are already searching for these signatures in the subtle warping of distant quasar light, hunting for the telltale flicker of a quantum halo at work. But here's the twist: quantum gravity itself remains one of physics' greatest unsolved puzzles. We still don't know how to reconcile Einstein's theory of relativity with the quantum world, and until we do, dark matter halos might be hiding secrets we're not even equipped to ask about. Every anomalous rotation curve, every unexpectedly diffuse core, could be a clue pointing toward a deeper quantum reality, one where the universe's largest structures are governed by rules written at the smallest scales imaginable. The quantum halo hypothesis isn't just about filling gaps in our knowledge. It's about peering into the abyss where gravity and quantum mechanics collide, where the invisible architecture of the cosmos might be built on foundations we're only beginning to glimpse. And if we're right, the answers won't just reshape our understanding of dark matter, they'll redefine the fabric of reality itself. The Milky Way's dark matter halo doesn't exist in isolation. It's just one invisible thread in a sprawling cosmic tapestry, woven into a structure so vast it defies comprehension. Welcome to Laniakea, our home supercluster, a gravitational metropolis spanning 500 million light-years and containing over 100,000 galaxies. And just as cities shape the lives of their residents, Laniakea's immense gravitational pull orchestrates the motion of every halo within it, including our own. To understand the Milky Way's place in this grand design is to see dark matter not as a local phenomenon, but as the hidden architecture binding the universe's largest structures together. Picture Laniakea as a colossal cosmic watershed, its gravitational currents funneling galaxies toward a mysterious center called the Great Attractor, a region of space so dense it pulls entire galaxy clusters into its grasp. The Milky Way, along with the Andromeda Galaxy and countless others, is caught in this slow-motion river, drifting toward this unseen focal point at over 600 kilometers per second. But here's the twist: the visible galaxies are just the tip of the iceberg. The real force guiding this motion is dark matter, its halos interlacing like roots beneath a forest, their combined gravity sculpting the supercluster's skeleton. Mapping these interactions reveals something startling: halos don't just passively coexist in superclusters. They communicate through gravity, reshaping each other over cosmic time. When two halos pass near one another, their mutual tug creates tidal streams, stretching their outer layers into faint bridges of dark matter. The Virgo cluster, Laniakea's most massive knot of galaxies, shows this in action. Its central halo acts like a gravitational wrecking ball, distorting the halos of smaller galaxies as they fall toward it, leaving behind smeared trails of stars and gas. These cosmic fingerprints hint at a hidden dialogue between halos, a silent negotiation of mass and momentum unfolding over billions of years. But Laniakea's halos aren't just responding to local forces, they're also relics of the universe's infancy. Simulations suggest that superclusters began as faint overdensities in the primordial dark matter web, their halos growing hierarchically as smaller structures merged. The Milky Way's halo, for instance, likely contains the shredded remnants of countless smaller halos, each swallowed during galactic collisions. These mergers aren't clean. They leave behind subhalos and tidal debris, creating a nested structure reminiscent of Russian dolls. The Sagittarius dwarf, currently being torn apart by the Milky Way, is a living testament to this process, its dark matter strewn across our halo's outer reaches like breadcrumbs marking a violent past. The most mind-bending revelation: Laniakea itself may not be permanent. Superclusters are transient, their halos destined to be ripped apart by dark energies accelerating expansion. In the distant future, as the space between galaxies stretches beyond the reach of gravity, the Milky Way's halo could find itself isolated, adrift in an ever-darkening void. Until then, it remains entangled in Laniakia's dance, a single strand in the universe's grandest web. Studying these interactions isn't just about mapping the cosmos, it's about decoding the invisible forces that have shaped our corner of existence since the dawn of time. After decades of hunting for dark matter, building underground detectors, launching space telescopes, and scanning the cosmos for any trace of this elusive substance, we're left with a haunting realization: we still haven't found it. Not a single direct detection, not one definitive signal to prove what makes up over 85% of the universe's matter. It's as if we've been chasing a ghost that refuses to materialize, no matter how sophisticated our tools become. This isn't just a minor setback, it's a crisis creeping into astrophysics, forcing us to ask an uncomfortable question: what if we're searching for the wrong thing entirely? Theories abound, of course. Weakly interacting massive particles, or WIMP, were long the leading candidate, with experiments like LUX Zeppelin and Xenon 1T scouring underground tanks of liquid xenon for the faintest recoil of a dark matter collision. Yet after years of silence, the parameter space for WIMP keeps shrinking, squeezing hope like a collapsing star. Actions, another favorite, remain equally elusive, their hypothetical existence dangling just beyond the reach of our magnet-equipped detectors. Even sterile neutrinos, those shadowy cousins to the particles we know, have failed to show themselves in the debris of particle colliders or the whispers of gamma-ray telescopes. The longer this drought persists, the louder the whispers grow. Maybe dark matter isn't a particle at all. Enter modified gravity, the rebellious idea that what we've been calling dark matter is really just gravity behaving in ways Einstein never predicted. The most famous of these theories, modified Newtonian dynamics or MUND, suggests that on galactic scales, gravity doesn't fade as quickly as Newton's laws dictate. Instead, it gets a subtle second wind, mimicking the effects of invisible mass without requiring any. It's an elegant fix for some of dark matter's thorniest puzzles, like why galaxy rotation curves stay flat far beyond where visible matter should allow. MUND even predicted the bizarre rotation of some dwarf galaxies years before observations confirmed them, a feat cold dark matter struggled to match. But MUND isn't a silver bullet. It stumbles spectacularly when faced with the bullet cluster, where gravitational lensing clearly separates from visible matter, leaving dark matter's fingerprint in plain sight. Proponents counter that even modified gravity might have hidden layers, tweaks to space-time curvature, or undiscovered fields that could explain these anomalies. The debate rages on, with each side brandishing its own successes and failures, locked in a stalemate that leaves the rest of us wondering, is this a battle of evidence or of paradigms? The truth might lie somewhere in the chaos between. Perhaps dark matter and modified gravity are pieces of a larger puzzle we've yet to assemble. Or maybe we're missing something even more fundamental, a cosmic variable so alien to our intuition that we haven't even thought to look for it. After all, history loves to humble us. Just as quantum mechanics shattered classical physics or relativity upended Newton's clockwork universe, dark matter's stubborn silence could be the prelude to another revolution. Until then, every null result, every unexplained anomaly is a breadcrumb pointing towards something deeper. The halo's ultimate riddle isn't just about what we haven't found, it's about what we haven't imagined. And if the past teaches us anything, it's that the universe rarely conforms to our expectations. It thrives on surprise. From the ghostly invisibility of dark matter halos to the bizarre missing satellites that defy our simulations, we've journeyed through 25 of the universe's most tantalizing enigmas, each revealing just how little we truly understand about the cosmic scaffolding around us. Think about it, halos that spin like cosmic whirlpools yet leave no trace of their motion, dwarf galaxies that should be drowning in dark matter but somehow float nearly empty. The eerie coincidence that dark matter and dark energy's densities mysteriously align in our cosmic era. And let's not forget the phantom halos, structures so diffuse they've never sparked a single star, yet linger like ghosts in the void. Then there's the quantum twist, the mind-bending possibility that halos aren't clumps of particles at all, but shadows cast from higher dimensions or flickering quantum foam we can't yet measure. Add in the rogue black holes that might lurk in their cores, the way supernova blast halos into puffy, distorted shapes, and the looming threat of dark matter's ultimate decay, and you've got a puzzle so complex it's humbling. But here's the thing, every mystery isn't just a gap in our knowledge, it's a doorway. The cusp-core debate could rewrite galaxy formation. The feedback loops between stars and halos might reveal how galaxies live and die. Indirect detections, faint whispers could crack dark matter's identity wide open. Even the sheer weirdness of pure dark matter galaxies forces us to ask, are we missing an entire hidden universe silently shaping the one we see? So now it's your turn. Which of these 25 cosmic riddles grabs you the most? Is it the holographic halo hypothesis that bends reality itself? The dark stars that might glow in our telescopes right now? Or the chilling possibility that we've been chasing a ghost that doesn't exist? Drop your thoughts below because the hunt isn't over. New telescopes, simulations, and experiments are peeling back the darkness layer by layer, and the next breakthrough could come any day. Stay curious, stay awestruck, and keep looking up. The universe's greatest secrets are still waiting in the shadows. P.S. Want to dive deeper? Hit subscribe, we're just getting started. The day dark matter's true face is revealed, you'll hear it